My name's Colin. I'm a VP and Distinguished Engineer at Amazon Web Services. I joined AWS in 2008, been here a while. Helped build a bunch of AWS services that hopefully you're familiar with. And what I'm going to talk about today are lessons I've learned from working with teams and observing teams who build some of our highest available services and the most highly available parts of those services. All the lessons today come from the data plane parts of our services. So, sometimes we can debate what's a data plane, what's a control plane, what are kinds of planes, propagation planes, and so on when it comes to the systems and services that we have. But what I mean by data plane is the part of our systems that is used the most, right? So if I take a service like EC2, the data plane for EC2 are the instances and making sure that instance stays up and that networking packets can get to and from it, and that EBS data storage is working and so on in real time. Those are the really, really critical parts versus something like the control plane, which is maybe launching a new EC2 instance or tearing down an EC2 instance and so on. And the first category tend to be much, much more critical, and we tend to pour or have to pour a lot of attention to detail and scrutiny into how those systems are built to get the reliability levels that our customers need. A lot of what I'm going to talk about today, we've got articles that go into even greater depth at the Amazon Builders Library. These are articles, really deep technical articles, written by first-hand experts, folks who actually built Amazon Web Services, write these articles, and they go through a review and editorial process, and we get them as readable and helpful as we can, and we dive into all sorts of nuanced details that are important to building highly available systems. We have articles on things like caching, retries, fairness, safety, and more. And if you want even more detail on things I'm not going to cover it all today, I encourage you to go there. It's a really, really great resource. I love it. But what I am going to go in today is, it's kind of my mission that everybody who came or everybody who watches this talk can leave with some tips or mental model or something that hopefully will stick in your mind that is really genuinely useful for building highly available systems. Now, every system is different. And while there are some techniques and tips and tricks that are in common and can apply to almost any system, a lot of the nuanced detail is very, very specific. So to make sure we get some good takeaways, I'm going to focus in part on some of the higher level lessons and the kind of forms of insight that genuinely apply to kind of any development process or any highly available system. And but we're also going to cover some super practical, like nuts and bolts, technical techniques that we do try to use in our systems and show the benefits that they bring. And just to keep things interesting, we're going to interleave these. So we're going to go back and forth between the two. So whether you're a hands-on builder, writing code, shipping systems, or whether you're an engineering leader or a principal engineer or even a business leader, hopefully there's things in here that will be useful and to take away. And so I'm going to start by very literally going beyond 5 nines. And what I mean by that is just thinking a bit more deeply than the traditional nines model itself allows. Because we want to be, when we're reasoning about building or designing highly available systems, we have to be careful about what components do we use, or what reliability level do we insist on for certain subsystems, because that all adds up to our overall availability. And in general, the traditional 5 nines model or N nines model, it's kind of crude and doesn't really give us enough. So you're probably familiar with the very traditional pattern of, you measure the uptime or availability of a system, maybe once a minute or something, and determine, is it up, is it down, is it fully available, is it degraded or whatever. And you can translate that into the number of nines that system was available for. A system that has 2 nines of availability can have up to 3.5 days of downtime or impact in a year, which is quite a lot, all the way up to 5 nines or even more 9 systems. And 5-9 system, you're talking 5.5 minutes per year, which is it's pretty aggressive. That's a very high level of availability at that point. And this model is useful. It's great for measuring overall business impact and value. Right? It does very succinctly summarize, well, how available was that system in a year? How often did I have to work around it? All of those things. You can see these baked into business relationships and SLAs and so on, often are expressed in terms of numbers of nines. But it's also a very low fidelity measurement. It doesn't really give us any insight into how the system is going to perform. And it's not so great for systems design. Some of the challenges of the nines model are, well, what about partitioned and cellular systems, right? Kind of nines can easily capture, a binary state, uptime versus downtime, but it's harder for it to measure partial availability, right? And at AWS, we've been partitioning all our systems since, we launched a second region. We have independent, isolated copies of each service in every region. And as far as I know, we've never experienced a global outage of any service across all regions. So every time we're talking about an issue or impact, it's already partial by that measure because it's only impacting one region out of many. And so some customers are having an absolutely fine day because they're in different regions, different locations, but some are impacted. But the nines model doesn't capture that as easily. Another challenge with the nines model is it's hard to pick a good time duration to measure over. Modern services, like the kind of cloud services that we operate, can now typically go many, many years in a region without having a single incident. There are extreme examples of that. So the Route 53 data plane, so that's the part of the Route 53 DNS service that actually hosts domains, answers DNS queries so that websites stay online. I was part of the team that built that. And when we were building it and launching it 12 years ago, very early in the beta program, I put my own personal domain right on that thing. It was the very first domain hosted on Route 53 was my own personal website. It's not a very high traffic website, but I owned a domain and I figured I might as well, start somewhere, drink my own champagne and put it on the service. And in over 12 years that's been running like that, I've never even once experienced not being able to have my domain resolved. That whole time it's worked. And the 5 nines model, I don't even know how many nines that is, right? It's really hard to capture. And part of the challenge here is that the nines model is really just a simple summary statistic, right? It's just a single number that's trying to describe a complex data set. One of my favorite papers is a statistical paper where the authors produced these, data sets that are radically different. One looks like a T-Rex, and the rest look like these other interesting shapes, but they all have the same mean, the same median, same standard deviation, and a bunch of other summary statistics where they're all the same thing. And the point of the paper was to get across something that is commonly taught in the very first lecture of a statistics module, which is you should plot your data. You should look at how it looks, don't just focus on the means and averages and so on, because it won't give you much insight. So we can apply the same technique, right? But what really matters? What is it the thing that we really, really care about? Because personally, I don't think nines tells you that much. And I think the thing that really matters to most customers, engineering leaders, and systems designers is how long can an interruption last and how often can that happen? And something I've done as a practice and seen work really, really well is to approach every systems design with this frame of mind and this frame of conversation. And so by talking to a team and just asking them, don't ask them, well, how many nines are you? Ask them, well, what do you think the longest event you could have would be? And how often do you think that could happen? Because that's just much more useful, actionable data. As a business owner, that tells you whether it might be an acceptable system or not. As an engineering designer, it tells you, well, now I know how long I might have to work around that system if it has an issue, right? Really, really focuses the mind. The durability industry has used this approach for a long time. Recovery time objective is kind of the standard number that industry uses for, I've got durable data. What happens if it goes down and I have to restore the whole system from backups? How long could that take, right? That's recovery time objective. And that's what they focus on. And I think it's a better thing to focus on. So we put all this together and focus on, well, what's the rate and expected duration of an incident or some kind of downtime or something like that. It's really easy to plot. I made up these data sets, but it's easy to plot them with almost any plotting tool. I used Excel for these. But the idea is to just pick some time ranges that you care about, right? Time durations, like let's say how often in a year are we going to have 1 minute interruptions? And this graph says for this fictitious system, 10 1-minute interruptions in a year. But then how often am I going to have an interruption that might last an hour, right? And on this graph, it's a log graph, it's about 0.5. And that's telling you, well, maybe every 2 years, right? You're going to have an interruption that lasts every hour. Straight away, you're getting kinds of insights that the Nines model just cannot give you, right? It can't expose that kind of information to you. Now this is still giving you binary data. It's just telling you about kind of if something's up or something's down. If we want to capture partial impact, it's really simple because this is a graph. We just add more lines, right? And so we can look at what are the expected rates of a 5% impacting event? How long could an event that impacts 5% of my resources or customers last? And so on. And just plotting the data like this gives you this insight. And then the next thing I do, I just take this data and I multiply it by the number of minutes involved. Nothing fancy at all, so we're just weighting it by minutes. And so now I get minutes per year by expected duration. And this is the kind of mental model and frame of reference I use when evaluating components and systems, right? Because this tells me so much, right? It tells me, okay, well, how reliable is that system going to be in this high fidelity way? But it also teaches me what to focus on, right? Like if I saw a graph like this for a system, I would know, well, I should probably spend more time focusing on the right-hand side of this graph, the longer duration events, because those are going to accumulate to more impact. And so that means refining operational processes, putting better failover mechanisms in place, and so on and so forth, right? Whereas if the left was higher, if we were a different system, and I'm going, you're going to have a lot of small interruptions, that's just probably telling me I need more components, I need more resiliency. But those are very different conclusions. But the number of nines could be exactly the same for those two radically different graphs. It's just simpler to talk about and reason about systems. And I find conversations like this enormous simplifiers. When I'm working with customers who have the highest availability requirements, where we're talking about, live market trading or safety critical systems and so on, we pivot into these conversations quickly, and it really helps us get to the meat of matters. And although the gold standard for this technique is to use real historical data, right, that accounts for the operational performance of a service and its team, and just use that to plot the graphs. Typically, services usually come with metrics and canaries and so on, and there are ways to get this data and build it. But even if you're building something from scratch, or you don't have that data, this even works with guesswork. I've done exercises where I've gone to teams, and I've just said, well, tell me your guess. How often do you think you're going to have a 1 hour, event? What's your guess? Do you think you could have one of those in a year? Do you think it's a 25% chance? And just that conversation, that style of conversation, right away gets you to actionable, interesting data that it's really hard to talk about with the Nines model. And by the way, engineers' guesses, they tend to be right. And no matter what you ask them about, they have an intuitive sense for this, at least the experienced ones. When you plot out these graphs, they're very different for a cloud service or an on-premises database or an on-premise application or low-level physical infrastructure. Even when they might have the same number of nines, they have very different shapes to these graphs. And so you have to accommodate that in your resiliency plans around these systems. I just find that endlessly fascinating. Richard Feynman famously applied this technique, this kind of like, just go ask the engineers, in his Appendix F that he wrote to the Challenger disaster report, where he literally just asked all the engineers involved in building the components for the Challenger rockets, what do you think the failure rates are like, all this kind of stuff. And he added up the numbers, and he got to an overall failure rate of about 1 in 100 for the space shuttle, which tragically turned out to be pretty much on the nose. Two space shuttles were lost in just around 200-ish missions. That stuff works. But there's other challenges with nines. There's other reasons why I try to avoid the kind of naive nines model when we're doing systems design. It's that it comes from mechanical and civil engineering, and it's kind of based around failure mode analysis that doesn't easily apply to our field. Physical components, you can test a bolt or a screw, over and over and over again under all sorts of different conditions and see how often it fails, and that'll tell you the failure rate of that component, and now you know how many bolts you need to put in something to make sure that it's safe. But our field's a little different. Firstly, our failures are recoverable. As an industry, pretty much every failure has always been recovered from. I don't know of any real outage or downtime at any company anywhere really in this whole field where they've had a permanently disabling event, right? So that's not at all like physical components. So recovery time really matters in a very different way. And another is that software systems and distributed systems, they tend to have nonlinear interactions and even positive feedback loops in different places, and much more state space than simple physical components, and all sorts of ways that makes them fail in kind of dynamic ways. A simple example of that, classic example, you want to suspend a weight. Well, you've got a chain or a braid, right? Everyone knows, famously, a chain is only as strong as its weakest link, right? It's an idiom. And so when you do the nines equations for these, it's a slightly different formula, right? The availability can go down for the chain, but go up for the braid, right? Because one piece of rope can save the day as far as a braid is concerned. And if you do the math, you add the numbers, you'll get lower availability for the chain than for the braid. And I've seen people apply this to distributed systems and systems design. And they end up getting disappointed. Like, it doesn't really work. A simple example of this, I'll go back to my DNS example. DNS is a relatively simple service. It's been around over 40 years, and its design hasn't changed much in that time. And you have a service that answers DNS queries, websites stay online, right? So it's very natural to think, well, I really care that my website stays up, so I'm going to use 2 or more DNS providers, right? I'm going to put my domain on Route 53 and another DNS provider. Great. And you go, well, I'm getting some biodiversity. They probably have different software, different networks, different people. It's very unlikely they would break at the same time, right? So it feels like the braid, right? But the problem is, in practice, it turns out it's like the chain, because in practice, DNS resolvers can't easily work around even one of your providers out of N being down. And so if one of your DNS providers has a bad day, then you have a bad day. So you end up actually doubling your fault rate, not having it, the opposite of what you intended. Or another simple example is if you rely on your DNS provider to be able to make timely changes, because that's what you use for your failover process. Again, you're going to get half the availability rate if you're relying on 2 providers, because now you need those changes reflected in 2 places. And it's just not really obvious unless you've gone and done it and experienced it and seen what's going on. And my take is that the kind of systems we all build, they're more like cantilevers than chains and braids. And what I mean by that is every single one, it's kind of specific and has to be tested. Like, you've got to build maybe a scale model and really exercise it and learn everything you can about how it might fail and make sure that you've accounted for all the safety mechanisms and so on. And that's the kind of approach to take. We'll see a bit more of that later. But this kind of end-to-end testing is what's really critical to figuring out whether these systems are safe and reliable enough for whatever purpose we've intended. All right, now there are some techniques that are so general purpose, they're pretty much always a good idea. And I think the biggest one that we apply is to compartmentalize our systems, right? So I've already hinted at this a little. We run independent copies of every service in every region, right? They're not magically linked. There's no synchronous dependencies between them. And the idea is if a service is having a bad day in region A, that shouldn't have a knock-on impact and cause region B to have a bad day too. That would also defeat the utility of having multiple regions for failover. And we take this to the extreme. Like, this is our default design paradigm. This is how we build every service that we do. It's baked into our tools, into our design processes, into our principal engineer tenets, everything. Thou shalt not build a multi-region service unless it's extremely intentional, and we're very, very careful about how we do build those, right? We want to keep everything as separate as we can. But even inside the region, we want to do the same again, right? Inside the region, we've got availability zones. And where we can, we run isolated separate stacks inside those availability zones. So that there's a problem in availability zone, US West 2A here, we can just turn it off, fail over to the other availability zones for a while, right? Fix it, fail back, It's a really, really powerful technique. We take it even further. We build cells inside availability zones. So when a service is big enough, when it makes sense, we can start to have multiple cells of that service, more independent copies, and then partition the customers across those cells. Some customers are on cell 1, some are on cell 3, and so on. And so, maybe you make a change, it gets to one cell, but that change has an issue or something like that. You're only impacting a much smaller percentage of your overall customers than everybody. We take this to the absolute extreme with shuffle sharding, where you can do better again, right? So let's say we've got 10 cells. Instead of just saying, well, we're going to take 10% of our customers and put them on cell 1 and 10% on cell 2 and so on, what we do is we take each customer and we say, we're going to put you on 2 random cells, right? So one customer, they're going to be on cell 1 and cell 6, and another customer might be on cell 1 and cell 8, right? So those 2 customers happen to share one cell, right, cell 1, but otherwise, one's on cell 6, one's on cell 8. And unless both of your cells that you're allocated happen to be having a bad day, which should be very unlikely, you should be okay, because there should be some resilience built into that system, and you should be able to survive on the remaining cell. And firstly, this makes things, because you've got that built-in resilience, and because we're really careful about how we do things like deploy changes, just naturally makes faults way less likely in terms of actually impacting a customer. While it might happen, the idea is they won't notice. But even if they do, even if somehow an issue does get to impacting 2 cells, because maybe this issue was triggered by the customer, right? So maybe that's why those 2 cells became impacted. Maybe it wasn't change related. Even in that event, with just 10 cells and this method, 1/100th of your customers are impacted and share a fate. And those numbers get better and better and better the more cells you have, because this scales exponentially. It's based on combinatorial math. It's pretty cool. And we try to use that in many, many places we can. This is something we learned. This wasn't something that was baked into the very first systems that we built. We retrofitted it into many, but it's something we learned to do over time. And I think of learning to do things over time as actually the primary way that we really design systems. I think often folks can think there's some mythical reference manual somewhere that maybe someone someday will write that just has all the best practices you're supposed to apply for systems design. And if you read that golden manual and you learn all those things, that you will just come out knowing how to build the perfect system, right? And now every time you'll just, I've got to build this system, I'm going to use technique, blah, 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 blah. It does not work like that. It doesn't work like that in civil engineering, mechanical engineering, and it definitely doesn't work like that in distributed systems. And so our designs have to evolve. And we have to figure out how to learn lessons, figure out what might we need to iterate on a service, and push that iteration. Now, if you accept that, you can still push through, and you can ask most people, well, what do you think is going to be most key to a highly available system? And they'll almost always tell you, well, it has to be simple, right? Because if it's simple, if it's got fewer moving parts, there's just less things that can go wrong, it's going to be a more reliable system, right? Very intuitive, makes a kind of sense. But the problem is, what does simple mean, right? A unicycle has radically fewer moving parts than a bicycle, but it is not simpler than a bicycle. It's way harder to ride a unicycle. And while a unicycle might have 50% the chance of getting a puncture, no one's commuting to work on a unicycle, except in Seattle where I live, where there are, I do see a few people who do it. But in general, most people prefer bikes. Bikes are way, way more usable. They're a much better solution to human locomotion than a unicycle is, right? And what's going on there, even though it has more components? I think that's because solid designs, things that will survive and we can really use, it's not about just having the fewest moving parts, but it's having the fewest parts that are truly needed. And having a design that takes into account all of the trade-offs that have to be considered, right? So if unicycles, bikes, and nothing like that existed at all, and you were given that design challenge, you might end up with a tricycle, because you're like, well, that's intrinsically stable. You can learn to ride a tricycle in 5 minutes, whereas a bike probably takes a few hours, right? But tricycles are bigger and heavier, and they're harder to park, right? So no one really commutes on tricycles. A bike turns out to be this nice middle ground, right, where you get, it's very usable. Within a few hours, even a child can learn to ride a bike, and it is easy to carry places and park and has all those nice trade-offs. But all of those things, I think, would have to be learned. If you went back to, pre the 1800s and had never seen either of those things, I don't think there's a book you could read or any system you could come up with that you would pop out with a bike as the perfect design, right? These systems really, really do have to evolve over time, and it's that process of iteration that matters. And so the best thing we can do as designers is try to use, the best, most well-worn patterns that we actually know of and reuse them, because that's what's going to be most reliable. And AWS services are really strong examples of this. Every service I know of still has code from its day one launch. Certainly the ones I worked on, and I'm pretty sure the rest. And we actually have it as one of our principal engineer tenets, respect what came before. We don't want to be, a not invented here culture, or just rebuilding, re-architecting things for its own sake. That way lies madness. Instead, we try to leave things alone as much as we can. We add whatever business functionality we need to support new features and improve performance and do all of the innovation that we love announcing here at reInvent. But, other than that, we want to use our root cause analysis process, which is our COE process, to learn any lessons we can from any interruptions or events and reintegrate that at the lowest level possible into our systems. When we have something go wrong, we take those lessons and we bake it back into code in our tools and our systems so that we're not just relying on good intentions, and so that we can keep those antibodies around and kind of spread those antibodies into the next system that we build. So an example of that, something else that we learned is that there's all sorts of change and dynamism that can be happening in systems. And a real key to building highly available systems is to minimize the amount of change and dynamism, because risk is proportionate to change. I mean, every event is a change, right? Something changed. That's why it went from up to down, right? By definition. Now, I'm going to talk later about how we ring-fence kind of operational changes, configuration, software updates, stuff like that. But another kind of change that's much more challenging is load, right? A customer can have a busy day without being able to predict it or know that it's coming. And you can have big load spikes, right? And those load spikes can exercise systems to points they've never been tested at, or slow down different parts of those systems, and maybe that slowness isn't tolerated and so on, and cause issues, right? So we want to be able to wrangle that dynamism. And we have a very counterintuitive solution to this, which is to try and run some systems that are in key areas just at the maximum load all the time, no matter what the customers are doing, right? And that sounds counterintuitive because it sounds wasteful. I mean, this is all software systems, so it's not real waste. It's all just electronic bits flying around. But it just feels wrong as a systems designer. It's not how most things, it's not our human intuition for how things should work, but actually turns out to be much more reliable because you're reducing the amount of change in the system. It's just always operating in a known, tested, kind of reliable state. A simple example of this is, let's say we've got a really high availability critical control plane, data plane, we're in the data plane talk, like something like a health check, right? So let's say Route 53's health checks. So they're health checking your endpoints to see, well, is that health check currently healthy? Is the web server up? Is it not up? And report that status back and integrate that into Route 53 so it can do some kind of failover, right? That's kind of how it works. And if you were to design this, I think a natural, organic way most folks would design this is, well, we'll build a health checker and we'll keep health checking. And if the health check changes, if it goes from healthy to unhealthy, if we've got some state transition, then we're going to push a change into Route 53. Right? We're going to kick off a workflow and edit the DNS record. Right? If this, then that. Right? Very, very simple. But the problem with that is when you've got a busy day, when lots of health check statuses change, things get slower. Right? Because you just ask the system to do more work. Now it's trying to push more transitions, ask Route 53 to make more changes. So that's not how it works. What it's actually doing is using constant work, which is every health check, it's happening once every few seconds, no matter what, and then the status, whether it's healthy or unhealthy, goes through this summarization process, actually temporarily goes through an S3 bucket, that's why I've got that here. And then Route 53 is ingesting those health check statuses, no matter what, right? Every few seconds, Route 53 is getting all of those health check statuses, all of them. It doesn't know whether they changed or not, every single time. And so it wouldn't matter if one web server suddenly went from healthy to unhealthy, or if 1 million web servers went from healthy to unhealthy. This entire part of the system wouldn't care, wouldn't operate any differently at all, wouldn't get any slower. It's counterintuitive, but it just makes things incredibly reliable. It's just, I love that pattern. So the next thing I want to talk about is testing. Because I think, actually, the next two topics I'm going to talk about, testing and operational safety, are the #1 things that any team can do to actually improve the availability of their systems. In practical terms, it is those things that make the difference. Testing our systems so that we don't have defects, and having very rigorous operational safety processes so we avoid mistakes impacting customers. That is ultimately what the game is about. Now, Andy Jassy here at reInvent in 2016 gave us a great saying, which is that there's no compression algorithm for experience. And I'm a super pedantic engineer. I'm a really annoying guy to be around sometimes. And I remember thinking to myself, well, is that right? I mean, I can read a book, right? And then I've got the author's experience. Or I can go to a lecture, and then I've got the professor's experience and so on. But that's not what this is about. I really love this saying, because what it's really conveying is the kind of experience that comes from being through issues and events and learning lessons the hard way turns into habits, right? Turns into personal habits and organizational habits and things that we all insist on. And that's ultimately what shows up and drives quality. And I genuinely think there is no compression algorithm for that. You kind of, as a group, as a team, as people, there's a certain amount of, you just have to have seen some things to get that. And I think this applies to testing. Because I think of testing as a little bit of a different kind of compression, a little bit of a time travel trick. If we know that we're going to have to evolve our systems right? To make them the most reliable patterns. We want to speed up that process of evolution and run it as fast as we can. And the secret to that is lots and lots of tests, and lots of testing and lots of observability. And if you were to work at AWS and see inside what's going on in AWS service, you would see just enormous amount of tests. Typically an AWS service has thousands and thousands of unit tests, hundreds of integration tests. We've got pre-production environments that we run and simulate everything in, and then we've got all sorts of fancy testing. If you want a flavor of this, we've got an open source project, S2N, which is our SSL TLS library. And that is a data plane component. And that is a data plane team at AWS shipping that code. But it's all public on GitHub. And you can go look for yourself at just how many tests they have, and how many tests are constantly adding, and how tests are in every single code review. And it'll just give you a sense of the scale of what's typical. It's kind of like a view inside. It is an enormous amount, way more than I see in typical open source projects. I don't have too broad a view into elsewhere in industry to benchmark us against that. But all of these tests are integrated and automated. Every time I submit a code review, well, obviously it had to pass my unit tests before I'd even bother submitting it, because those run locally. But even after that, we're kicking off integration tests so that we're not going to waste the code reviewer's time on something that doesn't pass the integration tests. And if it gets through code review, we're going to do beta and gamma and other pre-production testing and more besides. And that's just what the team is doing directly. As an organization, every time we build a new region, which is quite frequently these days, we, several times before that region has launched, will use that region as full region scale, wind tunnel. It is a simulation environment, and we will go deliberately break some things. We'll say, turn off power in this availability zone, and then measure ourselves against that, and learn any lessons we can. It's the cheap way, the way without impacting customers at all. By far the better way to learn those lessons, and then reintegrate those lessons into how our systems are doing. We also have teams that work on automated reasoning, building mathematical models of our system that you can use techniques like symbolic execution to run that code through basically every possible input and confirm that invariants are held and so on. We also do fuzz testing, which is pretty similar. All of this is like time travel, right? You're basically simulating the code through all these code paths that you could never really see in production quickly, right? Until some day where you suddenly do. Way, way better to find that out using these mechanisms. And then we also have a lot of instrumentation and observability built into our systems. Typically an AWS service has tens of thousands of metrics and alarms configured on those metrics. And all of those sensors mean, as we deploy a change or an update to our system, if anything regresses across that whole thing, it's like this embedded sensor network that can tell us if there are any early warning signs that we just did something bad, or regressed performance, which could turn into availability issues and so on. We get this data all the time, right? So we can constantly run this iteration loop where we can get the data we need to reintegrate, and hopefully build a bike and not a unicycle, right? That's what this is about. Now, all this testing, it's great for building, software that has as few defects as possible. But it would mean nothing if we were then, cavalier or haphazard about how we just get that software out there. Right? Turns out, at least in our environment, I think many of our customers' environments, most incidents, most issues are actually just triggered by changes. Operational changes that needed to be made, configuration updates, whatever it was. Those are what can be hard to account for and cause problems. And it's in the name. Web services are services, right? They're live running operational concerns. They're not just code in an editor, not just a compiled binary sitting there, right? It's a live running thing. And it's interactions with people that are going to change its behavior. Sometimes customers, like we saw with load, but most times operators, right? So that's what we have to pay attention to. Now, we've made enormous investments in centralized deployment safety. We have an incredibly paranoid, incredibly rigorous process to deploying changes. Because we know that new code means new risk. As rigorously as we test it, we know there still might be code paths that a customer is going to be first to exercise. And so we only want to promote that software very cautiously. We want to be very gradual in how we expose that to customers, and we want always to have the ability to quickly roll it back, right? So that there's even a hint that something's wrong, we'll just roll back, figure it out, do some investigation before we proceed again. And it's really, really typical that if I check in some code, it goes through code review and so on, and does all those normal levels of testing that I mentioned all the way up to pre-production. But let's say it passes all of that. So we think it's good to go to production. We'll typically promote it only just to one box, where we'll run it for a while, observe all the metrics we can and confirm everything looks healthy, and then progress to one availability zone, and then one region, zone by zone. We never deploy to multiple zones at a time, because that would defeat the point of having availability zones. And only as we get more confidence in that change in software do we expose it, to a bigger and bigger radius of infrastructure. And that has turned out to be enormously beneficial. We're also at the scale at AWS where we just can't manage things by hand. I can no longer remember every AWS region. I just can't. And we also have regions I don't even have access to, just because of the way we work. And so it's just not really possible to operate an AWS service in a way where imagine you're logging into a box and old school, SSH commands and restart this and all that kind of stuff. It just doesn't work like that. It's all done through these centralized deployment systems and safety systems and tools and automation. Some of that's for security reasons. We want to have important safeguards around systems to make sure people can't just be accessing them. But a really great benefit of this is operational safety too. Not having access to things means it just makes it harder and harder to break them. And we've been ratcheting this up. We've been building systems that are hermetic, like the AWS Nitro system, for example, which just really has no operator capability at all. There's no login capability or general purpose administrator capability or anything like that. The only way to administer the system is through software deployments. And this automation first approach just means every lesson we learn, right, can be fed back into code, which is the best place to put it, right? It's, you have an outage, you have an incident, you learn the lessons you can. Well, one approach would be to go, well, we'll try harder next time, we won't make that mistake, let's tell everybody we know. That's a disaster. That's just good intentions. Teams change over time. Maybe somebody forgets, whatever, right? So we really want to be able to put that lesson into a tool that will enforce it rigorously, do it the right way next time, because that's what's going to produce the most enduring value, and that's how it becomes an antibody, right? That's baked into the system. We're never going to repeat that mistake. We're going to get the value of that lesson applied. And that's our philosophy to operational safety. We never want to see teams being, haphazard or, cowboyish about operations. We like to see things being meticulous and fastidious, and that comes with overheads. That's a pain, to be honest, an inconvenience to do things like that. So it's another reason why you want automation first, right? You want to be able to have the tools do all that. And so the last thing that I want to talk about is a property that I see in every team I've worked with that manages very high-stakes systems. So the systems I'm talking about, remember the slide at the beginning with all the service logos. I think it's fair to say at this point, those are internet-scale services, right? If they have issues, it's an internet-scale event, right? It is literally making news and so on. The stakes are pretty high. And it's natural and appropriate to be appropriately fearful of that, right? Take that very, very seriously. But we have to get things done. And fear, leads to the dark side. It's not a good emotion. It's not what you want, and it's not going to produce the most conducive thing. And team culture, culture eats strategy for breakfast, right? If you want a system that's being well designed, hitting a high testing bar, and hitting great operational safety, what's going to do that isn't going to be like a written document or a vision statement or some rules written somewhere that this is how you have to do it. What's going to rule the day is how the leaders on that team, the folks that people look up to, how they convey themselves, the tough decisions and calls they make, right? The time where they decide not to launch something because, that needs some more attention and some more safety controls, that's what really feeds into all of this. And that's what I see, right? These spaces have very high stakes, and that demands very high standards. And it takes elite teams to deliver on that. Typically on these teams, when I see the folks writing code, like testing and quality assurance and all of these things that are the mark of a high quality system, it's not something that they're budgeting exactly, right? It's not like central planning decided, well, this team needs to spend 50% more time writing tests because they're critical. So every sprint, they're going to spend this percentage of their time writing tests and so on, right? It's not quite like that. It's not the way that it works or is budgeted. Instead, it's more like they've learned over time that to operate in this space, they just have to have these good habits. And every time they write code, they write a test. They just couldn't imagine doing it any other way, right? Or every time they do an operational change, they do it the safe way because they just couldn't even imagine doing it other way. You couldn't, even with a gun to their head, you couldn't make them do it the other way. It's just not how they do it, right? And it's like the master craftsperson who's, perfectly shaving a piece of wood and paying real fine detail each time. And if you ask them to do it in a hurry, they just look at you like, well, that doesn't make any sense. And these folks know that if you cut corners and if you don't have these high standards, you're going to pay for it. You might ship a feature faster now, but over a year or whatever, you're going to pay for it because you're going to have issues and you're going to have to come back and fix things, and that's not fun. And so what you tend to see in these teams is that they have really, fearless environments, and they're very supportive of each other. And when I say that these teams are elite, I don't mean, it's not about like, oh, well, we only hire the top 1% of the top 1% or anything like that. That's nonsense. It is, any person can be elite in the right environment with the right support infrastructure and the right culture around them, right? It's just about what the group insists. If you went and worked, for the fanciest hotel in the world, within days they'd be telling you, yeah, you got to polish every speck of dust. You got to make the bed perfectly. Like, that is our level of standard. That's what it demands. And they would just get that into you really quickly, right? And it's kind of like that. These teams, just how they do it. And they don't tolerate anything less, but in a very supportive, collegial way. And this is really, really important because when people are afraid and then they don't support each other, and when they just compete with each other, critiques and criticism gets buried, right? But you don't want that. You want these are high-stakes systems. You want every risk, every possible criticism raised, open and vocally, so that we can learn about it and potentially do something about it, investigate it and all the rest. And that's really, really key. So, every single one of these teams, I've been to their happy hours and parties, and they're all very supportive of each other, and it's just a fun, nice environment to be in. And I don't think that's a coincidence. I don't think it's a coincidence that it takes that. And so something I pay a lot of attention to, when I'm trying to keep an eye on a broad set of teams, is kind of where are they in a virtuous cycle that looks a bit like this, which is that, a good technically fearless team, they insist on high standards. And that means they produce things that are maintainable and operable. And that in turn makes that space attractive, because the folks who value quality, they can spot this stuff a mile away. They can see, oh, that team over there, they know their stuff, or they really insist on high standards. I want to be part of that. And by the way, if you're early in your career, I think the number one thing you should always do is find a team like that, a team that will insist on higher standards. And early in your career, in the short term, it can be harder to get promoted on a team like that because they have higher standards, right? You might not make it to the next level as quickly. But by God, over 10, 15 years, like the duration of your career, that early experience of getting all those high standards kind of into you pays off enormously, right? Because then you can bring that everywhere else. And there's a vicious cycle version of this too, right? If the opposite happens, right? If you've got poor standards, well, you're going to build a system that's unmaintainable, right? And that's rapidly going to backfire. People are going to get paged. They're going to be overloaded. It's not going to be fun. People might even leave. That's going to make it even less maintainable because now there's fewer people to handle all those pages and so on. And this can spiral. It's not fun, right? And there's unhappiness. And now maybe when people are unhappy, they're not going to be as supportive. So you really, really, really want to be in the positive cycle. And I always tell people, if a team ever does get into the unhappy state for some reason, and as a senior engineer or an engineering leader, you're asked to go in and help them, job number one, insist on high standards. Start there, because you can always do that. You can always come in and say, okay, general amnesty, everything we're doing until today, like it's in the past, it's over with, but starting now, we're going to have high standards. and that'll get the wheel turning, because folks will pick up on that, and it helps people care more and generate more happiness and so on. And I really look out for that, because I actually think it's at that cultural level that we can have some of the broadest impact that ultimately leads to higher availability systems. Hopefully that doesn't sound, too hippie-ish or something from me, but I think it's very real. So key takeaways. There's a few hopefully speckled throughout the talk. Hopefully something's going to stick in your mind that you'll remember someday that it's helpful. But the ones I want to highlight that I think are particularly useful is if you're working on highly available systems or systems design in general, and just try to push past the traditional nines model. Try to have a mental model that gets a little bit deeper and really tries to understand the potential failure characteristics, including duration, right? I didn't mention it earlier, but this is how we measure extreme weather events, for example. Right? We talk about a 1 in a 100-year flood, right? Which is sadly becoming more common because of climate change. But this is actually a really common dominant approach to safety engineering that for some reason or another is kind of overlooked in our field, but has a lot of value. The next takeaway is I want every builder to kind of have enough humility to realize that we don't really get to design systems. Systems outlast us. They go through many iterations and many teams and so on. And really it's our job to shepherd its evolution. And that when we approach it with that philosophy, we should try to figure out how can we speed up that evolution as much as possible, how we can get as much data and have the most rigorous ways to integrate that into our innovation and iteration processes so that we collect all these antibodies and build them in, because that's what's going to have enduring value. And the last takeaway is it's really elite, happy, supportive teams that are going to be the key to anything. If you've got a team that is burying risks or is unhappy for whatever reason, you're just not going to have enough kind of human slack to really be able to operate and build systems safely. And that, I think, just ends up being really, really key for this field. Hopefully everyone took some takeaway there. Thank you all for coming. It's been a real privilege to speak to you, especially here in such a beautiful location.